In this video, we will learn how to compute the covariance matrix. If you remember, the motion model we have covered looks like this, where this is the F matrix, and we assume that we are in a constant velocity. This vector, on the other hand, is called u, and it assumes that we have a constant non-acceleration, ax and ay. But what happens when we don't have the acceleration, when we need to approximate the acceleration in another way? What we will do is consider this vector as stochastic noise. And now we will see how to deal with this stochastic noise. The stochastic noise is called Ni, and we can assume it's distributed normally with zero mean and the covariance matrix Q, where the vector Ni contains ax and ay, the acceleration in the x and y axes respectively. How are those acceleration distributed? We don't know, but we will define them as distributed normally with a zero mean, because this is the safest policy, and the variance of sigma ax square and ay square. I want to remind you, the variance is the variance which describe how much those acceleration distributed in the population. If you want to track a pedestrian, we can see how pedestrians walk usually and extract from this the standard deviation or variance of the acceleration. Given this data, how can we extract the Q covariance matrix? Vector Ni is the same acceleration vector. The acceleration vector you can write as a product of two matrices. The left matrix, which we will name G because this is the deterministic matrix. All the elements in matrix G are known, delta t. On the other end, the right matrix, which we will call A, is a random matrix. We don't know the ax and the ay because they are the unknown accelerations. If we define the matrix as follows, we can write it as G times A. Right now, what we have left to do is to calculate the covariance according to the following formula. But note, because Ni is distributed with a zero mean, the element of E of Ni, or the expected value, is back to zero. If instead of Ni we write G times A, and instead of Ni transpose we write G times A transpose, we can get the following thing. But this is way more interesting because G, since it's deterministic, is not in the expected value anymore. So what we end up with is G times the expected value of A times A transpose times G transpose. The expected value of A times A transpose is a covariance matrix of A, where on the diagonal we have the sigma ax squared and sigma ay squared. On the sides we have sigma ax and y. And it is very logical over here that there is no relationship between the acceleration in the x or y axis. Therefore, we can zero those elements. And then you can write Q in the following way. If we now multiply everything, Q looks like this. This matrix will add to the P vector when we calculate the noise. If you have approximated values of sigma ax squared and sigma ay squared, you will get a much better estimation of the state of the system since you know how to handle noise accurately. Good luck!